Hello everyone! In this video, we will be taking a look at Prism spectral analysis code, PrismSPECT. With PrismSPECT, users can easily investigate how plasma spectral properties change with different plasma conditions. This type of analysis can be useful for a variety of applications. PrismSPECT is a 0D single-cell collisional-radiative spectral analysis code designed to simulate the atomic and radiative properties of laboratory and astrophysical plasmas. A few examples are shown here, including the plasmas found in an inertial confinement fusion experiment seen here in the upper left, where the spectra from argon-doped and the target fuel are used as diagnostics for plasma conditions. In the upper right is an example of a PrismSPECT simulation of plasmas used in laboratory astrophysics experiments, for example, in the study of solar opacities. The lower left is a time-dependent PrismSPECT simulation of the spectra in a short-pulse laser experiment observing the cold K-shell emission of copper caused by hot electrons. PrismSPECT also has industrial applications. For example, simulating plasma light sources in extreme ultraviolet lithography as seen in the lower right. PrismSPECT is one of Prism computational science's analysis codes. Given atomic data, PrismSPECT is able to simulate the spectra ionization fractions in atomic level populations for a set of plasma conditions. In this video, we will be using PrismSPECT for two examples. In the first one, we will look at an absorption spectra for an aluminum foil under LTE conditions. In the second example, we will look at argon-doped deuterium under conditions relevant for inertial confinement fusion experiments. Let's do the first example now. The first tab is the Plasma Elements tab. This is where you add different elements to your spectra. In order to add an element, all you have to do is click the Add button right here, and a periodic table will pop right up. From this periodic table, you can select different elements to add. For our example, we will take a look at aluminum, so we choose aluminum from the periodic table. Now, we need the right atomic model for our simulation. Depending on your plasma conditions, you might only include certain atomic levels in your model. We will talk about custom atomic models in a future video. Some standard models are included in this default list, and we will use backlighted K-shell spectroscopy in order to include transitions from which we expect to see absorption. The second tab is the Simulation Type tab. Here, different parameters are added to your simulation. The first parameter is time. You can either have a steady-state solution or a time-dependent solution. For our example, we will go with the steady-state solution. Next, plasma variables need to be set. For our geometry, we will go with the planar geometry. The electron distribution will be a single temperature model for an electron temperature. The density will be defined as the mass density, and the size of the system is going to be the delta L, which means linear size. We won't be adding a proton beam, and we won't be adding extra plasma pressure models or external radiation sources. The third tab is the Plasma Properties tab. This is where you can define which independent variables you will be changing your spectra with. PrismSPECT can add up to 2 different independent variables at once. This defines a set of plasma conditions for the simulation. For our current simulation, we will just be using a single independent variable. There are 3 options: plasma temperature, mass density, and thickness. We're interested in seeing how the spectra changes as you heat the material, so we will choose plasma temperature. Here, you also define different plasma parameters. Because we're changing the plasma temperature, we need to supply a range of values. To do that, we're just adding a table with values of 50, 70, 100, and 150 eV. We will also be supplying a constant mass density, in our case 0.27 grams per cubic centimeter, which is 1/10 of the solid density of aluminum, and a constant thickness, 2 microns. The fourth tab is the Atomic Processes tab. Here, you choose which atomic population models you will be using. For these conditions, LTE is a valid approximation. The fifth tab is the Spectral Grid tab. Here you can find the photon energy range of your spectrum and also how many points along the continuum. These continuum points will increment logarithmically. As you increase the number of continuum points in your spectrum, its resolution will increase. However, the time it takes for the simulation to run will also increase. For our example, we will use a photon energy range of 50 to 1500 eV and will use 2000 points in the continuum. Note that each emission line will receive the additional photon energy points so that they will be resolved. We can leave the default for this at 13, the number of points per line transition. The sixth tab is the Output tab. Here you define what type of output information you want for your simulation. For this example, we won't have any special output. Now that we've gone through each of the tabs of PrismSPECT, we can simply click the Run Simulation button, provide a run name and file location, then click OK and the simulation will begin. First, let's take a look at the spectral output page. When you click Spectra, a new window will pop up. Here you can see different spectra for a given plasma temperature. However, let's change it to transmission to see some absorption features. The transmission spectrum lowers towards 0 where the plasma is optically thick. You can use the magnifying glass to zoom into those features. You can also hover your mouse over the temperature field and scroll through the temperatures to see how the graph changes. Here we can see a clear effect of the shift in ionization as we increase temperature. At a higher ionization, the transitions are occurring at higher energies. We can obtain more information through the ionization window. If you look at this list, let's find the ion with the highest fraction. Now let's plot the 5 ions around that aluminum 7 ion. Here we can see the temperature dependence for these individual ionization stages. You can also look at the ionization distribution at specific temperatures. To do this, change the x-axis quantity to ionization stage. Then, select the element, in our case aluminum, and click the arrow button to see the ionization distribution at this temperature. You can overlay the distribution for another temperature by changing the value and clicking the double arrow. You can see the ionization shift to higher levels at higher temperatures. Now, we'll look at another example, this one relevant for inertial confinement fusion experiments where an argon dopant is used for spectral diagnostics of the plasma conditions of a deuterium fuel. First, let's add argon and deuterium with a number fraction of 0.001 for argon and 0.999 for deuterium. We will keep the default atomic model as emission K-shell spectroscopy. For the second tab, let's use the steady-state solution, planar geometry, ion density, and size by length with no proton beam. For the third tab, we will look at variation in plasma thickness, and we will see some effects of opacity on the plasma emission. We will use a plasma temperature of 1500 eV to see some emission from the K-shell ions. We will keep it relatively dense at 5 times 10 to the 23 ions per centimeter cubed. Let's change the thickness units to microns. For our thickness table, we will have a minimum value of 50 microns, maximum value of 150 microns, with 11 grid points. At these conditions, LTE is not a valid assumption, so we will use non-LTE kinetics for our atomic processes tab. We will discuss advanced simulation options in another video. For the spectral grid, we will use a range of 3000 to 4500 eV range for the photon energy grid in order to see the K-shell emission features. We can keep 200 points for the continuum and 13 additional points for each transition. For the last tab, output, this time we will be adding two ions, argon-17 and 18. This will let us separate out spectral contributions from these two specific ions. Now, let's run our simulation. Let's take a look at spectra first. We can change the y-axis to log scale. Let's zoom in on these two lines, which we'll see are the 2-to-1 transitions. You can scroll through sizes to see how the spectrum changes. Let's put it at 50 and add 100 and 150 to the same plot. Right away, you can see that the line on the left is changing approximately proportionately with size increase, but the line on the right is not changing as rapidly. Let's see if we can determine what these transitions are. If we click on the Show Transitions table, let's find these energies in the list. We will add some filters first. We choose the argon-17 ion and hide satellites transitions. The lines we zoomed in on previously are these 2-to-1 transitions here. By default, transition labels include just ion names. We want to be able to see details of the transitions. Let's click Edit Graphics Labeling Parameters to make sure that we can. We uncheck ion name and check term symbol and change the configuration field to include all subshells. Now we can label them on the spectrum by clicking Grid Line and Label. The one at this lower energy we can see is the triplet P upper state that results in a forbidden transition, which is an intercombination line. The oscillator strength for this transition is small. This is why it isn't absorbed as much as the 1p upper state transition. So, they do not see the same amount of absorption with increasing size. Indeed, if we look at the optical depth plot, we can see that the optical depth of the resonant singlet-to-singlet transition is much higher than that of the intercombination transition. Let's look at this a little more with the line intensities window. Let's add each of those transitions into this list of lines and bands. We will repeat the process of filters and add both of them to selected transitions and the list. Then, we can plot the ratio of these lines by putting the resonance line in the numerator and the intercombination line in the denominator. Now, we can plot the ratio. Since the line is decreasing, this means the resonance line is increasing relatively less than the intercombination line. We can dive even further for a specific atomic level by looking in the ionization window. Right-clicking our upper level, 1s1, 2p1, 1p1, and selecting Get Transition Rates by right-clicking. This is akin to selecting a row in the matrix of transition rates, and all non-zero rates are included in this table. This shows the in and out of our selected level for all non-zero transitions, showing collisional as well as radiative rates. If you scroll all the way to the right, you can see the total rates in and out as well as the net rate. Let's look at one more thing in the spectra window. We can separate the contributions from the individual ions which we chose at the beginning of the simulation by clicking Spectral Components and selecting argon-17 and 18. Here, we can see the contribution from argon-17, which are helium-like, argon-18, which is hydrogen-like. This concludes the introductory video of the PrismSPECT series. Thank you for watching!